Okay. Any questions before we start? I'm sure there's at least that one, like, did I make a mistake last time? Hopefully I amply confessed I did. So, happens all the time. So we'll try to clarify those things on Slack. I'll try to, put a note in the video if I make an error. And so what I really should have done is just listen to you guys a little bit more and not rush right at the end, but these things do happen. We're gonna pick up again where we were last time, but I want to show you another argument for coming up with distributions of order stats. So far what we've seen for coming up with the distribution of probability is we came up with that combinatorial argument. And we can always do that. It just kind of enumerates this big sum. And if we wanted to come up with a density function, we just differentiate that. But as we move to joint order stats, coming up with the joint cumulative is not something that we do. We express joint densities, and then we say how you can integrate over different ranges of this. It's not always from the left tail of, I'll say for a bivariate distribution. It's not that we sum over the left tail. What does that even mean in bivariate land? In one dimension, everything's easy to order. That's why we'll talk about cumulative distributions over one-dimensional thing, because we know which direction we sum over. But as we start moving into 2 dimensions or 3 dimensions, that's not a convention that we assign. So usually it's nice to just count the density so you can see which ranges you want to sum over. Does that make sense? So it's better to come up with the density functions. But I showed you the reverse, where we came up with the cumulative, and then we came up with the densities. So saying that, it's nice to have multiple arguments for different things. Let's look at a couple examples. So 2 quick examples. The max and the minimum. And we can compare this to what our formula is supposed to give us as well. And so a lot of these problems, when I give you a midterm, I'll see 3 different ways of solving a problem. And it's really nice. I get to see all these different variations, how you can go about solving a problem. But I think you want to be thinking about that too. Are there different ways to solve the problem? And it gives you kind of your own check. Both of these different methods should come up with the same solution. If I don't get the same solution, I know I've made a mistake in at least one of those. So I like to think about it that way. Here's a different way to think about the distribution of the maximum. So it's distribution. So when I say distribution, if I'm saying it correctly, I mean probability. So we might want to know what's the probability that xn is less than or equal to some value right here. So I'm going to assume that this is a continuous distribution that gives us all the xi's. So xi's coming from little f, and I can integrate little f, and that's going to give me cap f. So that's the cumulative. You're going to ask me what are the ranges of x. This is just arbitrary. So I'm just going to say you're going to integrate from the left tail to some value, what I call x. I'll remind you, this x is not that x, it's not that x. They kind of look similar, and so I'm using a recycled notation. If you don't like that, you can do something like this. Minus infinity to y. Change that to y, but I'm just going to change it to x anyway, eventually. Okay. So the probability that the max is less than something, I can just use a pretty simple argument to convince myself this is the same thing as all the xi's are less than or equal to x. So what I mean is x1 has to be less than x. x2 has to be less than x, and all of them have to be less than x. That's what it means for the maximum to be less than x. So what's the probability of each thing being less than x? It's this thing, f of x. And so this right here is just equal to f of x raised to the nth power. So we don't need our formula to derive that, but we'll make sure our formula does derive this as well. So something for you to think about. If I wanted the density for this example, then all I have to do is take a derivative. So, and that's just going to be the derivative over this thing, so I'm just going to have n, I'll write it down in 2 steps. So this is going to be n, drop my exponent, decrement it, upstairs, apply the chain rule. So the derivative of cap f is, of course, little f. And so, what itty-bitty formulas or a picture to derive this? Because I'm just thinking about what it means for the maximum to be less than a value. The minimum's no harder than this. So, I might want to know probability of x1 less than or equal to some value x. Of course, in order to apply a similar argument, I need to bound this in the other direction. So I need to think about the flip of this thing because all of these values are now bigger than something. And so I'm going to write this out just a little bit differently. This is going to be 1 minus the probability that x1, my minimum, is greater than some value x. I'll take out the equal sign. It doesn't matter. This is a continuum that I'm thinking about. And so if I inadvertently left that minus, that equal sign, it still means the same thing. But we'll be polite and get this right. And so this is the same thing as saying the probability that all the xi's are greater than x. I got 1 minus this thing. And so that's going to be 1 minus cap f raised to the x power. So I'm just taking the complement and taking the complement again. So what's the probability that each one of the xi's is greater than something? It's 1 minus fx. The same exact argument. So if I want the density, same thing. x1, x, I just take a derivative over everything. I'll do this all in one step. Derivative of that is 0. There's still a minus sign sitting out in front of here. So this is minus n times 1 minus fx. Decrement my exponent, n minus 1. Apply the chain rule to minus cap f. So that's little fx. And then there's a minus sign in here. So that gets rid of that minus sign. And that's my density function. So different ways to think about this. If you wanted to think about any other order step, you need to do that cumulative thing that I wrote down. And they have that formula expressed in the book as a big sum. But basically, you're just taking that tail probability. So we worked with this example of out of n things where n was 6, and I wanted to know the 5th order statistic, I had to add 2 things together. So if you end up looking at the 4th order statistic in that example, you would have to add 3 things together. So that's how that would work. And then you can work through the density. Of course, for a joint order stacked, that sum method isn't going to work for you. And so what I did last time is I tried to draw you a picture that you can remember so you can remember this formula for life. Let's just redraw this picture I did out in here last time. So for the ith order statistic, I'll call that xi. So that's the ith largest thing. I know that there's some number of things over here. We got this part right last time. And so this is I minus 1 things over here. So we're not counting this I thing, we're leaving that separate. And then there's some number of things over here, and we made a mistake. What's the correct answer? How many things are over here?
N minus I.
N minus I. We'll see how good you are in a minute, but basically we're going to apply this argument again in the joint case. So what's the probability of being over here? It's F. I'm going to call this value right here, I'm just going to call it X. So I have two different names for this thing. It's Xi is the random variable, and the value that it takes on, I'm just going to call X. It's just my dummy argument. So the probability of being to the left of X, any one of these points, is Fx. Probability of being over here is 1 minus Fx. And we're not thinking about probabilities, we're scaling the probability to an interval. Usually we call this, maybe make an interval x minus epsilon and x plus epsilon right here. And so I can talk about the probability of being in that interval, and I can scale that interval to its interval length, and I can take a limit to some instantaneous rate. So we're thinking about density functions, and so not my probability of being right here, my density, that's little fx, and that's that. How many things are right here? One thing. There won't be any other things right there. So the formula for density of xi, this is just going to be this. So I have to account for everything right here. How many different permutations of everything are there? So there's n things in the entire data set. So there's n factorial permutations of everything. I'm not going to distinguish any of these, but I will distinguish them from those. I won't distinguish any of these from each other. So how many different rearrangements over here are there? It's I minus 1 factorial. How many different rearrangements are there over here? N minus I factorial. Again, I don't care what the labels are on all of these. This could have been the first draw that I saw, this could have been the 6th draw, or vice versa, and it wouldn't matter. So we're just counting over those different enumerations. So I could write 1 factorial down right here if you wanted to. I always leave that out. So how many different rearrangements are there of that one thing? 1 factorial. But if I added all these together, this plus this, so I minus 1 plus n minus I plus 1, that's going to be equal to n. So just a sanity check, we've counted every point in here. And if we would have done that sanity check last time, we would have realized we'd made a mistake. We didn't add up to n. So if I ask you to do this with like 3 order stats on a midterm or something like that, you can draw a picture and start counting everything in the bins, and that's probably the hardest part of that problem. So then I look at f of x, the probabilities, I account for those. So I've got I minus 1, things that happen with probability cap f. Then I have 1 minus f of x, how many things happened, n minus I, and then I've got my very last thing that I need to account for. That's f of x. And that's my formula. Again, if you want a more formal proof of this, just make this a probability, scale it to its interval length, and take the limit. And so you'll just be accounting for these probabilities, take the limit, and you get the density back. And so I think that's probably the swiftest argument. My picture ultimately says that. At least it's trying to say that. Okay, let's just do another sanity check. And just make sure this formula gives us this stuff that we came up with completely different rationale. Our thought process was a little bit different. Also, you can verify that summation argument that we used before. We could have derived these distributions right here. Of course, you'll probably, for the minimum, want to complement out so that you don't add everything together. So that you don't add every single point. It's easier than that. There's only one thing that you need to add in that, as long as you work in the complementary space. So you can verify that, use that argument, I'll let you do that. But just let's make sure that this formula matches what we derived. So, fxn. Call my dummy argument x. We'll have to change that for joint order stats. But this is going to be n factorial over n minus 1 factorial. I is 1. I is n in this case. And then I have n minus n factorial. I don't write 1 factorial down. This is 0 factorial, which is equal to 1. So times f of x, n minus 1, 1 minus f of x, n minus n, and then I have my density function. If we simplify all of this, n factorial over n minus 1 factorial is just n. This is f of x to the n minus 1 times f of x, little f of x. And voila, we get the same thing back. So again, lots of ways to do this problem. On a midterm, it's not uncommon for me to say something like derive the minimum or something like that. And if you can't do it, then I know you aren't paying attention. So, because it's one of the easier problems if you know how to do it right. And again, lots of ways to get to these distributions. We'll work through an actual example in a minute. We could do the same thing, might as well, for the minimum. So if you ever get stuck, draw the picture, write down the formula, just stare at it, and plug things into it. That's what I do if it's 9 o'clock in the morning and I'm trying to do something. So, n factorial over 1 minus 1, I is 1 in this case. So same sort of thing, n minus 1 factorial, and I don't write down the 1 factorial. So times f of x, 1 minus 1, 1 minus f of x. This is going to be n minus 1 times this little density. So again, we match what we had before. N factorial divided by n minus 1 factorial is n. This thing is 1. This is going to be 1 minus f of x, half f, n minus 1 times little f. So we match what we got before. So lots of ways to do this problem. It's the other ones, not the max and the min, that are a little bit more cumbersome to go through. What I usually do, if I didn't know that summation argument, is I would just derive the density and then I'd integrate over it. So again, another way to do the problem. Lots of ways to think about order stats. Let's look at joint order stats. They have this in the book. They have a nice argument all in paragraph form that you can read through for what the distribution or the density for joint order stats is. You can read through that if you want. If you want a different argument from what I'm giving you. When I first saw that, I was like, how the heck am I ever going to remember any of this? And so I need to understand it. And ultimately, for me, understanding it means I can draw the right picture that I can remember. So let's draw that picture. So I want to look at the joint order stat. I'll say X. Again, all these Xi's are coming from some distribution. F, I'll call it X right here. And they have cumulative distributions, integral f of x dx. I'm going to integrate from the left tail to some dummy argument fx. But I'm just going to write this down as cap f. So again, minus infinity out to x. I've recycled my notation. If you don't like that, replace that with a y, replace that with a y. This x is not that x. So one thing I look for on things like midterms and homeworks and so on and so forth is if you integrate something, that argument can't be part of your integration. You've integrated it out. So don't be fooled. This is a different x. So let's draw the picture. So I want to look at the joint order stat for the I biggest thing and the j biggest thing. And I'm going to say I is less than or equal to x is less than j. So what that means is xi with the braces is less than or equal to xj. I'll point out to you, if you did have highs in all of these formulas, it doesn't make any difference. You can verify that to yourself. So if I had two things, let's say I had a list of 4 different elements. Let's say the elements were 1, 2, 2, and 3. So if I called 1 x1 with the brace, the minimum, x2 is 2, x3 with the brace is also 2, and x4 is 3. So if you define it that way, these formulas work out great. So no issues. So let's say this is the ith largest thing right here. This is going to be the jth largest thing. I'm going to have to give these notation. I can't just use x because there's 2 values here. So I'm going to use what the book uses, and I'm going to watch my language while I do it. So U and V. Okay, so let's draw our picture. How many things are over here? Probably the easy one. I minus 1 things. Let's do the other easy one. How many things are over here? And minus 2. The hard one.
J minus
J minus I. We've got a J minus I plus 1. J minus I minus 1. So that's right. So how many things are over here? Not that one. J minus 1 things are over to the left of that little point. So I'm going to get infinitely close to that. J minus 1 things, and then I'm going to subtract off these I things, if you want to think about it this way. So this is J minus I minus 1. How many things are right here? 1. 1 thing right there. So if you add these up, I've got I minus 1 plus this right here plus that. So you can go through the mental exercise. It all adds up to 1 or n. Again, add those ones in. So that's this one and that one. I's cancel, J's cancel, Hopefully you can do that initially. Okay. So we've got all of our things. Probably not very good. Word, elements, realizations, samples. Lots of words there. So what's the probability of being over here? There was one time a helicopter landed on the road. I wasn't in this classroom, but I was right down the hall, and one of the military helicopters came in and dropped off some high-flying kernel. They thought it'd be a good idea. Pretty hilarious. They were doing the thing that they do with the t-shirts on the drill field. Have you ever seen that? Save the Next Girl. So it's a big promotion. Watch out for that during the spring. It's actually really nice. You can see all these different colored t-shirts all over the place. And the helicopter just threw that thing all over the place. People were scrambling. Got written up in the newspaper. It was pretty surreal. So we just took 5 minutes to watch. Okay, I think it's quite enough. Okay, so we'll get rid of.
Question.
Yeah.
I decided to check the sum of the n-1,
Uh-huh.
n-j, so we get n-2, so.
Yeah, but you didn't count the one here and the one there.
Alright.
So those are the extra ones. So there's two things, so there's these two extra values. But good job. Okay. So this is f of u. I'm a seasoned pro. F of u. What's this one? 1 minus f of b. Those are those probabilities. What's the probability in here? F of b minus f of u. Okay, very nice. So now we can write down our formula if we're prepared to do that. I kind of like this because it scales. You can do it with any number of these things, just as long as you're willing to count. It really is that more hardcore mathematical argument with limits. We're just not going through the work to do it. So again, what's the density right here? The instantaneous probability is I take this limit, little f of u. Again, these are all the same random variable, x, x, x. We might want to just write that in to remind ourselves. And this one right here is f of b. They didn't come from different distributions. Okay, let's write down our formula. I want to remind us that xi's are IID. If they weren't IID, none of this would work. So I couldn't just do this exchangeability sort of argument and count over everything. So it required all of these to be IID. The order stats are not IID. They come from the same sample. I need to order everything to figure out what their positions are. So if you ordered n-1 things, and I asked you what's the third biggest thing out of n, you wouldn't know until you put that last one in there. So it could shift everything around. Might not perturb what the third largest thing is, but if it's one of the smallest things in your set, then it will perturb it. You don't know until you see the whole sample what the order stats are. Okay. So f, xi, I'll write it out this way, xj, if you want, putting that down in the subset. It's a little bit clumsy of notation, but just so you know what this density corresponds to. And then we've chosen these arguments, u and v. I probably should have picked x1 or xi and xj would be nice, so I could remember what they meant. That's what I would probably do. But we can remember, at least for this small set, what u and v are. So, let's just work through the combinatorics. There's n factorial things. So, I can rearrange the I minus 1 things over on the left in I minus 1 factorial ways. I've got a j minus I minus 1 factorial ways. I can rearrange the stuff in the middle. And I've got n minus j rearrangements of the stuff over on the right. So let's count for our probabilities. Our probabilities are f of u. That's to the I minus 1. Again, that's for random variable x. So we'll distinguish what the f's are on the board. I've got f of v minus f of u. Again, they're associated with the same random variable. This is raised to the j minus I minus 1. Then I have the other probability, 1 minus f of v. That's going to be n minus j times. My glasses and my mask are failing me right now. All I see is a blur. And then I have to write down my densities. So little f of u, little f of v. And they're all associated with the same random variable. And that's it. So let me just query you guys. Did I get that right? Looks like all the terms are there. And I probably need to be a little bit polite and just remind everybody that u is less than or equal to v. And since it's a continuum, we really need it to be less than if we're going to be making sense of all of this. So I'll just get rid of the equal sign. Okay. They have this hard problem in the book for the range and the mid-range. And we've seen that problem and we've even drawn that distribution. So we didn't work through that distribution of the range and the mid-range. Let me remind you what the problem was. We didn't work through any of that. We actually took a rather computational approach to seeing that distribution. But we could work out its formula directly. So, example. This is in the book. We won't get through this whole example right now, so I'm going to ask that you read through the example and see the difficult parts of the problem. So this was xi's are coming from a uniform, and I'm going to call it 0 alpha before I call this 0 theta. So the same exact problem that we were studying before. The book uses alpha, so I'll just stick with alpha. IID, there's n draws from this distribution. So we know what the density is. F of x is equal to 1 over alpha. F, I'll say cap F, the cumulative distribution is going to be x over alpha. So that other example I had where the density was 1 cap x and 3 or 4 of you said, oh, that's a uniform distribution. You think that it's a uniform because you're recognizing the CDF. And in my case, I was making that for PDF. It's a different thing. I just noticed that fools at least several people every single year I present that. They'll jump on it. It looks like a uniform. No problem. Okay. This one is. Okay, let's see if we can apply this formula and try to figure out what the distribution the joint distribution of the range which is xn minus x1, and the mid-range. And I'm just going to call it V because the book calls it V. It's rather annoying to me. So I can never remember what V means. But if it were called M, I'd probably remember. We'll just leave it as is. This is xn plus x1 divided by 2. So the order statistic. So the difference between the max and the min is the range, and the average, which is a really weird statistic. Not quite sure why you would ever want to use this. I've never seen this in practice, the mid-range. So it's weird because I'm using the order statistic and averaging over them the extrema to come up with an estimate of the middle. And probably if I were using the order statistics, I'd probably look at the median. Saying that, it does make a fun calculus problem for the book, and I think that's why they present it. So it's worth walking through. I wish this had some very strong relevance, but I've never seen this used. Saying that makes for good problems. Okay, so we want to find that. So we need a couple steps. So step one to do this is find the joint for x1 and xn, and then we transform. Step two, transform. I want to point out this is a one-to-one relationship. So these are just linear equations. And so I can immediately transform the distribution that I can derive using this formula over here. So there's a couple steps to the transform, and we'll work through it. But again, look at this in your book so that you can do this problem swiftly. The hardest bit is figuring out the bounds of everything. So when we simulated, what we did is we drew all of our xi's from little f. We did that n times. I sorted everything, computed the max and the min, and I had those samples so I could directly transform them and come up with samples of the range and the mid-range. And then I repeated, and I repeated. And that's a rather difficult computational process because I have to generate all n values. Instead, what I maybe could have done is sample directly from this formula if I knew how to do it. So I do know sampling algorithms for pretty much anything. And so it's just a question of how long it takes to run them, but we could certainly speed up that computation by applying this formula. Or applying the formula that we're going to get once we derive this and then transform. So let's write down the joint distribution. So joint for x1 and xn, this is just going to be n factorial. I'm going to have n minus 1 factorial. That's my n minus I. So I'm going to have n minus 1 minus 1 factorial. That's my middle term. So n minus 1 minus 1. This is wrong, right? That's a 1 minus 1. And this one is n minus n factorial. So we've got that bit. That's probably the hardest part of the problem, is just making sure that you know how many things are assigned to each thing. So I'm going to write down my density functions right here. So I have f of x times f of x. I'll say f of u and f of v for these two different spots right here. I'm going to re-nickname those. Just so I can remember what's what. I'm going to call this value right here x of 1. I'm going to call it x1. Don't confuse that for the first element of the draw. I'm just going to do that. It's just a favor to us. So x of n I'm going to say its value is xn. Again, this is not the nth draw from my distribution. It's the position of the nth largest thing. So this is going to be our density function for each one of these is 1 over alpha. That's for x1. For xn, there's no x's that appear. It's uniformly distributed. It's always equal to 1 over alpha. So I've got 1 over alpha squared for my densities. Those are the things that are drifting off at the end of my formula. Now I need to come up with my probabilities. So this is going to be x1 over alpha, and that's raised to the 1 minus 1. So that's going to cancel out. Then I'm going to have xn over alpha minus x1 over alpha. These are my cumulatives. And I'm going to have n minus 1 minus 1. So j minus I minus 1. So that's n minus 2. And then this will cancel out as well, but we'll write it down anyway. This is xn over alpha, 1 minus this thing, raised to the n minus n. So I also need to tell you that x1 is less than xn. Those are less than alpha. That's less than alpha, and this is greater than 0. So you have to be careful in these situations where you have these values bounding each other. So it's going to put interesting constraints in your transform. So at the end of the day, this is n factorial divided by n minus 2 factorial. So that's n times n minus 1. We're going to get all of these. This is also n minus 2 right here. This alpha right here is going to factorize out n minus 2 times. And there's 2 more alphas over here. So I'm going to get 1 over alpha to the n. So again, I'm factorizing out the n minus 2 of these, and I'm combining them with those 2. So that's going to be 1 over alpha to the n, xn minus x1, raised to the n minus 2, and I think that's everything. So again, xn bounds x1, and they're also bounded. So that's our joint density. So to do the transformation, we need to do a couple steps. So Eric asked for lots of examples on transforming joint distributions. Here's one more. Yeah, the goal is to get you guys to ask the question right before I'm about to lecture on. So that's perfect time. Okay, so what we need to do is we first have to solve for xn in x1. We have to come up with the inverse transformation. We need to figure out the Jacobian, and then we have to do the hard part and express the bounds and everything. So the range is equal to x1 minus xn. Oops, the other way. And the mid-range is going to be xn plus x1 divided by 2. Let's just do the inverse transformation first and solve for xn and x1. So we can do that. So I'm just going to rewrite this real quickly. 2 times that. And then maybe what I'll do is I'll just add these together if you want. So this is 2 mid-range plus the range. And this is going to be 2 times xn. When I add those together, these x1s cancel. They add up to 0. And so that means that the maximum is equal to the mid-range plus the range divided by 2. We'll do this again. So I'll just say the range is equal to x n. Actually, let me do it this way. xn plus x1. So 2 times the mid-range is that. And the range is equal to xn minus x1. I'm going to subtract these from each other. So this is going to be 2 times the mid-range minus r. Let's subtract those. That's the 0. And I subtract a negative, that's adding. So 2 times the min. So just some quick solves to come up with the inverse relationship. So this is going to be x1 is equal to the mid-range minus r over 2. Okay, so what we're going to do with those is we're going to plug them into these positions right here into our formula. But we also have to express the Jacobian, and we have to look at the bounds of everything. Sam?
You don't have to do this simultaneously, right? We could just solve for r and then set v equal to like.
I could have done it that way. Okay, exactly. I did it like how I got taught in like algebra class in high school.
Okay.
So I probably would do it a little bit differently if I were just sitting at my own desk. But yeah, absolutely. However you solve for it, as long as it's right. It's okay. Okay, so could take my Jacobian. What I want you to look at though, instead, right now the Jacobian works out B1. We'll verify that next time. So, but I want you to look at this function. And we drew this out before. So this is 0, this is alpha, right here, and let that be alpha. So I just want to point out some things. There's lots of ways for the range to be 0. That means x1 and xn are equal to each other. And so if they're the very minimal value, then the mid-range will be 0. So if they're 0, if they're both 0, and if they're both alpha, which is never going to happen, but it's at least part of the space, then the mid-range is alpha, if they're both the biggest values. And so I can take on any value in this interval right here. I'm just doing this a little bit conceptually. We'll do it more formally next time. So there's only one way for the range to be alpha, and that's when xn is equal to alpha and x1 is equal to 0. So this is xn is equal to alpha and x1 is equal to 0. So again, I'm using intuition because I know what these random variables are. But you should be able to do this even without knowing any of that. So these things connect right here. And that's that triangular shape that you saw last time. So what I did is I drew samples in this range using a very expensive computational procedure. So try to verify what these lines are next time, and we'll pick up with that very mini calculus lesson. So the hardest part of any sort of transformation of integral problem. So we'll work through the Jacobian. The Jacobian's 1, and then we'll have a joint distribution for the range and the mid-range. In the book, they show you some integrals for the marginal distributions. One of them splits into 2 functions, and one of them is easier to integrate over, and they relate it to a beta distribution. So read through that passage because I'm not going to talk about all those margins. I might say something about them briefly, but you'll want to work through those integrals. So try to do that at home, and I'll see you on Friday. We'll pick up there, and then we're going to start the delta method. So I'm going to have to show you some preliminaries for the delta method, i.e. Taylor expansions. So do me one more favor and look up Taylor's theorem. And Taylor's theorem doesn't just tell you how to come up with a polynomial approximation, but it says something about the remainder. And the last term bounds the error in that approximation. And so we're going to be coming back around to that. And if you don't get to that, I'll try to explain it. Okay, guys, thanks a lot.